At the dawn of the 20th century, science was on the edge of transformation. The world seemed orderly. Newton's laws of motion described falling apples and orbiting planets. Space was thought to be absolute, and time was believed to flow the same for everyone, everywhere. Then came Albert Einstein. In 1905, and again in 1915, he proposed ideas so radical that they rewrote the fabric of reality itself. He showed that time can slow down, space can bend, and gravity is not just a force but a warping of space-time. This revolutionary framework is known as the theory of relativity. It changed physics forever, reshaping our understanding of the universe and paving the way for modern technology. From GPS satellites to black hole research, Einstein's insights still guide science today. This is the story of how relativity changed time and space forever. To understand Einstein's revolution, we must first imagine science before relativity. In the 17th century, Isaac Newton formulated laws that described motion and gravity with remarkable accuracy. His equations explained how planets orbit the sun, how tides rise and fall, and how objects move on Earth. Newton's universe was like a grand clock. Space was fixed, an infinite stage where events played out. Time was universal, ticking at the same rate everywhere. Gravity was a force pulling objects together across empty space. For more than 2 centuries, Newton's laws were unchallenged. They powered the Industrial Revolution, guided navigation, and explained astronomy. Scientists believed they had unlocked the secrets of nature. But by the late 19th century, cracks appeared. Experiments with light showed puzzling results. The speed of light seemed constant, no matter how the observer moved. This clashed with Newton's ideas of absolute motion. At the same time, new discoveries in electricity and magnetism revealed forces that did not fit neatly into Newton's framework. The universe was beginning to look stranger than expected. It was into this world of unanswered questions that Einstein stepped, reshaping physics with a vision that would change everything. In 1905, Albert Einstein published his special theory of relativity. At its core was a simple but astonishing idea. The laws of physics are the same for all observers, and the speed of light is constant, no matter how you move. This principle shattered centuries of belief in absolute space and time. If light's speed never changes, then space and time themselves must adjust. Special relativity showed that space and time are not separate. They are woven together into a single fabric called spacetime. Events that seem simultaneous to one observer may not be simultaneous to another. Distances and durations depend on how you move. The theory introduced equations that linked mass and energy, culminating in the famous formula E equals mc squared. This revealed that matter and energy are interchangeable, unlocking the understanding of nuclear power and the energy that fuels stars. At first, these ideas seemed abstract. But over time, experiment after experiment confirmed them. From particle accelerators to precise clocks on airplanes, special relativity has proven true every time. Einstein's theory was not just mathematics. It was a revolution in perspective. It told us that reality depends on motion, that time and space are flexible, and that the universe is far stranger than we thought. One of the most dramatic consequences of special relativity is time dilation. Imagine 2 twins. One remains on Earth, while the other travels on a spaceship near the speed of light. To the traveler, time flows normally, but when they return, they find that far more time has passed for the twin on Earth. This is not science fiction. It is a real effect of motion on time. Time dilation has been tested with atomic clocks flown on airplanes and satellites. The moving clocks run slower compared to those on Earth, exactly as relativity predicts. Another consequence is length contraction. Objects moving at speeds close to light become shorter along the direction of motion, as seen by an outside observer. Together, these effects mean that space and time are not fixed. They stretch and shrink depending on motion. Relativity does not break the rules of cause and effect. Instead, it redefines them. It tells us that reality is relative, shaped by the speed and perspective of each observer. These concepts challenge our intuition, yet they are essential to modern science. Without accounting for time dilation, GPS satellites would drift off course within minutes, making navigation impossible. What began as a bold theory in 1905 now shapes the technology we use every day. After publishing Special Relativity, Einstein turned his attention to gravity. Newton had described gravity as a force acting at a distance, pulling objects toward each other. But Einstein saw something deeper. In 1915, after nearly a decade of work, he introduced the general theory of relativity. It redefined gravity not as a force, but as the warping of spacetime itself. According to Einstein, massive objects like stars and planets bend the fabric of spacetime. Smaller objects, including Earth and even light, follow the curves of this geometry. We feel this curvature as gravity. The idea was radical, but it was testable. In 1919, during a solar eclipse, astronomers observed starlight bending around the sun, exactly as general relativity predicted. The discovery made Einstein a global icon overnight. General relativity explained phenomena Newton's laws could not. It showed why Mercury's orbit shifts slightly each century, and it predicted black holes, regions where space-time bends so extremely that nothing, not even light, can escape. It also revealed that the universe itself is dynamic, capable of expanding or contracting. This insight laid the foundation for modern cosmology and the Big Bang theory. Einstein's vision turned gravity from a mysterious force into a geometric property of the cosmos. It was one of the most profound achievements in the history of science. To picture general relativity, imagine a trampoline stretched flat. Place a heavy ball in the center, and the surface curves downward. Smaller balls rolled nearby will spiral toward it, not because the heavy ball pulls them directly, but because the surface guides their path. In the universe, space-time is the trampoline. Planets, stars, and galaxies bend it with their mass, and objects move along its curves. This warping of space-time has real consequences. Light from distant galaxies is bent around massive clusters, creating cosmic lenses that magnify objects billions of light-years away. The ticking of clocks slows down near strong gravity, a phenomenon called gravitational time dilation. On Earth, this effect is small but measurable. GPS satellites orbiting high above the planet experience weaker gravity than clocks on the ground. Their time runs slightly faster, and engineers must adjust for this to keep navigation accurate. General relativity also predicts ripples in space-time called gravitational waves, created when massive objects like black holes collide. These waves were first detected in 2015 by the LIGO Observatory, a century after Einstein predicted them. The warping of space-time is not just a theory. It is observed, measured, and essential to understanding the universe. Among the most dramatic predictions of general relativity are black holes. These are regions of space-time where gravity becomes so strong that nothing can escape. Black holes form when massive stars collapse under their own gravity. Their mass is squeezed into a tiny region, creating a singularity surrounded by an event horizon, the boundary beyond which no information can escape. For decades, black holes were considered theoretical. But today, evidence is overwhelming. Astronomers detect stars orbiting invisible companions, gas heated to extreme temperatures as it spirals inward. And in 2019, the Event Horizon Telescope captured the first image of a black hole's shadow in the galaxy, M87. Einstein's theory also predicted gravitational waves, ripples in spacetime produced when massive objects accelerate. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting waves from the merger of two black holes more than 1 billion light-years away. These discoveries opened a new era of astronomy. Instead of just observing light, scientists can now listen to the universe through gravitational waves, revealing collisions and cataclysms once hidden from view. Black holes and gravitational waves are not just exotic predictions. They are real, observable phenomena that confirm the power of relativity and expand our window into the cosmos. Relativity also reshaped our view of the entire cosmos. Einstein's equations suggested that the universe could not be static. It must either expand or contract. At first, Einstein resisted this conclusion, adding a constant to his equations to preserve a stable universe. But in 1929, Edwin Hubble discovered that galaxies are moving away from us, and the farther they are, the faster they recede. The universe is expanding. This discovery confirmed what Einstein's theory had implied and gave rise to the Big Bang model, which describes the origin of the universe nearly 14 billion years ago. General relativity also plays a role in understanding dark energy, the mysterious force driving the accelerated expansion of the universe. Observations show that not only is space expanding, but it is doing so faster and faster, a challenge that continues to puzzle cosmologists. From the smallest particles to the largest scales of the cosmos, relativity provides the framework to understand it all. It shows that the universe is dynamic, evolving, and deeply connected. The theory of relativity did more than solve scientific puzzles. It changed how humanity sees the universe. Relativity showed us that time is not absolute, that space is not fixed, and that gravity is not a mysterious force, but the curvature of spacetime. It revealed black holes, gravitational waves, and the expansion of the universe. It gave us the foundation for modern cosmology. It also gave us tools for daily life. Without relativity, GPS satellites would not function. High-precision technologies, from particle accelerators to advanced imaging, depend on Einstein's equations. Relativity continues to guide the search for new physics. Scientists are working to unite relativity with quantum mechanics, creating a theory of everything that could explain the deepest mysteries of the cosmos. Experiments with black holes, gravitational waves, and high-energy particles may bring us closer to that goal. Einstein's legacy is not just his equations. It is the way he transformed our imagination. He showed us that the universe is far stranger and more beautiful than common sense suggests, and that curiosity and creativity can unlock its secrets. Albert Einstein once said that imagination is more important than knowledge. His theory of relativity proved this to be true. More than 100 years later, relativity still shapes science, technology, and our understanding of reality itself. It tells us that the universe is a living fabric, bending and stretching, filled with mysteries yet to be solved. As we explore further, relativity will remain our guide, pointing us toward new discoveries and deeper truths. This is how Einstein changed time and space forever. If you enjoyed this journey through the cosmos, make sure to subscribe for more explorations of the hidden universe.